Welcome to this series of video lectures for our Introduction to Plasma Physics course. Today we will have the first video lecture of a series of three dealing with plasma wave interactions. Plasma wave interactions, as we will learn as we go along, play a very important role in the whole field of plasma physics. Let's establish the goals for this first session. The goals for this session is, first and foremost, we will also help define a couple of parameters and a couple of electric parameters that are very important in the description of the plasma. Waves are responsible for the propagation of sound, and they're responsible for you being able to hear what I'm saying right now. We also have mechanical waves. Mechanical waves are basically what makes an equation that I have right here, this equation of motion that I'm going to circle right now, this one right here. Recall that it's actually not one equation but three. So let's write it down in components just to refresh your memory. So it says that dvx in dt, and that's going to be equal to q over m, and then we have the x component of the electric field plus the x component of whatever vector results from doing the v cross v product. Similarly, we're going to have dvy in dt, and that's going to be equal to q over m. Again, that's not changing because those are constants of the particle that we're talking about. And then we're going to write down ey, which is the y component of the electric field, times again my v cross v product, but now I need to extract the y component. And then dvz in dt, and that's going to be equal to, again, q over m, and then ez plus, and then the y component of the the z component of the cross product. So that equation that we have right there, it's actually three equations. Once we write down this equation for both ions and electrons, we can use these expressions for velocity. I'm going to get one expression for the velocity of the ions and another expression for the velocity of the electrons. And then I can take advantage of the fact that just for the sake of remembering things, for those of you who don't have your vector calculus vector cross v, and a quick way of finding out what this is just writing it in matrix form, and we write it as ax, ay, and az, and those are going to be the components, the Cartesian components of the vector A. And then I'm going to write the Cartesian components of the v vector right here, vx, vy, and vz. And then I'm going to write down here the vectors, the unit vectors along the three directions, I, j, and k. And basically, the result of the cross product is just taking the determinant of these, or something equivalent to taking the determinant of this matrix. So what I'm going to get for the I component is, I'm going to write the I component, and that's going to be equal to ay bz minus az by, and that's going to be the x component of the cross product vector. Now if you recall Kramer's rule, for the second column I'm going to have to write a minus sign because on odd columns I need to change the sign, on even columns, sorry, and that's going to be equal to the product of ax times vz minus bx x az, and my k component, or my z component, which is multiplying the vector k, that's just going to be AX BY minus AY BX. So recall, the only thing I did is whenever I want to calculate the I component, I basically eliminate these two, and all I do is multiply these diagonal and then subtract the product of these other diagonal. And I do it similarly for the other three columns. And this is going to be a very useful tool when we want to calculate things like the cross product of the velocity vector and the magnetic field vector. Once we know the expression for the velocity and we can plug it into the definition of the current density, we can go back to Maxwell's equations and actually find out that that is just equal to, like we said before, the density times the charge, and then the velocity of the electrons, and then I subtract the velocity of the ions because those two currents run in opposite directions. So on the other hand, I learned that the total current density is actually the sum of two current densities, like we talked a few minutes ago, which is the displacement current, the current associated with oscillations in the electric field, plus the conduction current, the one that's associated with mostly, or actually not mostly, but associated with the motion of charge. Now, I can actually write the conduction current as the product of two quantities, which is the electric field, E, and an electrical parameter of my medium that I choose to call the conductivity. And the displacement current, on the other hand, that's going to be equal to just the rate of change of the electric field with time times another constant, which is the dielectric constant of the medium. Now, it may not seem too obvious, but this expression that I have right here for the conduction current is actually the Ohm's law that we all love and know, the one that we learn in high school, which is, if you recall, if I want to calculate the current on a circuit, well, the only thing I have to do is calculate the voltage and divide by the resistance of my circuit, right? That's the Ohm's law that we all know and love. Now, the expression that I have here inside the rectangle is just another way of writing Ohm's law. Let's see how. This current right here, well, I can relate that to the current density. Performing an integral of the electric charge flux across an area will give me the total current. So this conduction current density is just proportional to the actual current running through the circuit. Now, the voltage, recall that the voltage and the electric field are also related. The electric field is just the gradient of the electric potential, or the thing that we typically call the voltage or the electric potential. So again, the electric field and the voltage are interrelated, and I can write them equivalently, and just the same for the current and the current density. Now the only thing that's left is this resistance of the current. Now we mentioned that this sigma parameter that I'm pointing at right now, that's just the conductivity of the material, and that tells us how conductive it is. So it is not too hard to imagine that the resistance of the material is just the inverse of the conductivity, or vice versa. The conductivity is just the inverse of the resistance. The more resistive the material is, the least conductive it is. So these two are just the inverse of each other. And there you have it. I have done the analogy between these definitions for the conduction current and Ohm's law. So going back to the total current density, I can write it as the sum of the conduction and the displacement. So it's going to be the sum of the pure conduction, the pure displacement current and the pure conduction current. But if I choose to describe my medium as just a dielectric with an effective dielectric constant, I can write it as an effective dielectric constant, epsilon, not epsilon naught, which is the vacuum. I choose to write it as epsilon and multiply that by the time derivative of the electric field.